So for Chapter 11, Day 7, we are going to talk about what is called the discriminant test. And the discriminant test is a way for us to look at various equations of conics, so parabolas, hyperbolas, and ellipses, that are not in standard form, and first determine what type of conic it is, and then we're going to look at how to then take that equation and rewrite it so that it is in standard form. And today we're going to be using the algebra technique called completing the square. So we'll walk through that process and how that comes into play when we are rewriting conics into standard form. So the first thing I want to talk about is what the discriminant test is. So the discriminant test is a way for us, again, like I said, to check the type of conic we're dealing with before we even start rewriting or even looking at a graph of the equation. So one thing I want to point out is you see this long equation here. We have ax squared plus bxy plus cy squared plus dx plus ey plus f. And in the equation we're dealing with today, not all of those terms will be in every equation, but I do want to point out that a will always be the coefficient of x squared, b will be the coefficient of any term that has an x and y in it together, c will always be y squared, and then d will be the coefficient of x, e of y, and f will always be the number that's by itself. Now if you look at the actual discriminant, the discriminant is something we've talked about in algebra before. It's usually what's underneath the radical when we are using the quadratic formula. If you remember, x equals the opposite of b plus or minus the square root of b squared minus 4ac. That's the part that's underneath the radical, and it's called the discriminant there too. But the idea here is if we check that value using the coefficients in the equation, if we get a number greater than 0, it's a hyperbola, less than 0, equal to 0, it's a parabola, and less than 0, it's an ellipse. So what I want to point out is, although we'll have other variables and other terms, we're only going to use a, b, and c for checking the discriminant. So we'll walk through the first example, and you'll see how that comes into play. So, like I said, DEF will be in the equation at times, but it won't be used to compute the determinant. So if you look at example 1, I first want to check what type of conic we are dealing with. So first thing I'm going to do is identify my a, b, and c value and then compute the discriminant. So a is going to be 1, because again, a is always the coefficient of x squared, so the coefficient is 1. B is the coefficient of xy. There is no xy term, so b is 0. And c is the coefficient of y squared, and there is no y squared term in my equation, so c is going to be 0. So b squared minus 4ac, I would put 0 in for b, 1 in for a, and 0 in for c. So what I'd get is 0 minus 0 or 0, and what that tells me is we're going to be looking at a parabola. And the reason why we want to identify that first is because that should give us a clue as to what the equation of a parabola looks like. And if you remember, there are two standard form equations of parabolas we talked about at the beginning of the chapter, and they are either x minus h quantity squared equals 4p times y minus k, or y minus k quantity squared equals 4p times x minus h. So if I look at my equation and those two standard form ones, what you'll notice is in them either x is being squared or y is being squared. If you look at our equation, we have x being squared. So the way we're going to approach this is we're going to keep our x terms on the left side and move everything else to the right. So if I do that, I would get x squared minus 8x equals y minus 19. So if I add y to both sides and subtract 19, and like I said before, what we're going to do here is what's called complete the square. And what that means is we're going to take what's on the left side and add something to it to make it a perfect square that will factor. So what I like to do is rewrite the equation like this, and I leave a little gap between the 8x and the equal sign, because I'm going to add a number there. And the way we figure out what number that is you take half of 8, so half of 8 is 4, and square it, you get 16. So if I add 16 to the left side, that is now a perfect square trinomial, so it will factor into a binomial squared. That's the whole purpose. But then what I add to the left side, I must also add to the right side in order to maintain an equation or maintain equality. So now I've completed the square, I do need to factor. And we did this back in back in first semester when we were talking about writing parabolas or writing quadratics in vertex form. It's the same kind of process here. So what the left side now factors into is x minus 4 quantity squared, and what I get on the right side is y minus 3. And this is almost exactly like one of the standard form equations we talked about. The only difference here is y is usually thought of as inside of a quantity with a number out in front. So if I wanted to, I could put this in a set of parentheses and put a 1 out front, and this would be the standard form equation for that parabola. So we look at the next example. It's going to be very similar in terms of the process, and we'll start by determining the discriminant, figuring out what type of conic it is, and then writing the equation. So A in this case is going to be 0, B is going to be 0, and C is going to be 1. Again, A is the coefficient of x squared. Since there is no x squared term, that's 0. B is the coefficient of xy. There is no xy, so B is 0. And C is the coefficient of y squared, so C is 1. So then in terms of the discriminant, b squared minus 4ac, I would get 0 squared minus 4 times 0 times 1. So I'd get 0 for the discriminant, which tells me we are going to, again, be writing the equation for a parabola. And then there are two standard form equations for parabolas, and they are x minus h quantity squared equals 4p times y minus k, or y minus k quantity squared equals 4p times x minus h. So if I look at the equation I have y being squared, and I don't have an x squared, so I'm actually going to try and make it look like the second one there. So what I'm going to do is keep all my y terms on one side and move everything else to the other side. And now what we need to do is complete the square on the left side. So what I'm going to do is rewrite that with a little bit of space in between the 6y and the equal sign, and think about what I need to add to make it a perfect square. And what you would do is take half of 6, which is 3, and square it, and you get 9. So now the left side is a perfect square, y squared minus 6y plus 9, that factors into y minus 3 quantity squared, and if I combine like terms on the right side, I would get negative 12x plus 12. And we are almost done with this one, writing it in standard form. The one thing we do have to do is simplify the right side so that I have x plus or minus some number with a inside of a quantity with a coefficient out front. And the way you do that is if I factored out a negative 12 from both terms on the right, I would get y minus 3 quantity squared equals negative 12 times the quantity x minus 1. And the reason we want to write it this way is if you think back to our parabola equations, from this equation now I should be able to identify my vertex, and then if I want to find my p-value, I would set whatever's out in front of the x quantity equal to 4p and then solve for p. So that's why we want to take that last step and factor out a negative 12 from both terms so that I have my x minus 1 quantity and the coefficient out in front. For the next example here, I'm actually only going to ask you to identify the conic. And the reason why is this one has an xy term in it, which is fine for the discriminant, but also makes it very difficult algebraically to complete the square. So instead, if I came across a problem like this, you might just be asked to identify the conic rather than going through and writing in standard form. So we're just going to do the discriminant part of this. So I'm going to identify A, B, and C. So A, B, and C, I would get 9 for A, it's in front of x squared, negative 6 for B, and 1 for C. So if I compute the discriminant here, I'd get negative 6 squared minus 4 times 9 times 1, so I'd get 36 minus 36, which is 0, which tells me that we are going to be looking, this is an equation for a parabola. And like I said, we're not going to try and factor or complete the square here because it's going to be fairly difficult with that 6xy term, but you still could look at the discriminant and see what the conic is. So for the next one, though, we are going to go through the whole process. So the first thing I'm going to do is identify A, B, and C so that I can determine what type of conic we have. So A is going to be negative 9, it's coefficient of x squared. B is going to be 0 since there is no xy term, and C will be 4. So if I compute the discriminant, I would get b squared minus 4ac and should give me a value of 144. And since that value is larger than 0, we have a hyperbola. So what we're going to do is rewrite this hyperbola in standard form. And one thing I want to point out about hyperbolas, hopefully you remember, is that the x and y quantities are both on the left side and our non-variable terms are on the right. So I'm going to try and reorganize this left side so my y's are close together and my x's are next to each other and both on the same side of the equation. Now in terms of the order of hyperbolas matters. So if you remember, it's either y or x squared first and then a subtraction sign in between. So if you look at my two squared variables, 4y squared and negative 9x squared, if I write my y squared first, or my 4y squared first, the minus in between there will be there when we write our equation in standard form. So I want to definitely write my y variable first in this case. So I'm going to move my terms around a little bit. So I'd get my y terms next to each other and my x terms next to each other, and then add 41 to both sides. And then I'm going to complete the square here. So before I do that, though, I have to have y squared by itself, because taking half of the middle term and squaring it only works when the coefficient of the squared term, in this case y squared, is 1. So what I'm going to do is factor out a 4 from both of my y terms. And I'm going to leave a little space here because I'm going to complete the square inside of that quantity, and you'll see how that works for our equation. And then if I factor out a negative 9 from my x terms, and again I want to factor out a negative 9 because that would give me just x squared inside of the parentheses. So I'd get x squared plus 2x. I'm also going to leave a little space there because I'm going to complete the square. And then when I complete the square, I have to think about taking half of 2, so it's 2y, so take half of 2 is 1, squared is 1, so that's where that plus 1 came from in that first quantity. And I also get a plus 1 in the second quantity by the same reason. Take half of 2, square it, I get 1. So right here, we might be thinking, okay, I'm going to add 1 to the right side twice. But the issue here is when I add 1 inside of the quantity, I have a coefficient out front. So it's really when I add 1 inside of my y quantity, I have a 4 out front. That's really like adding 4 to the left side, because if I distribute it, I'd get 4y squared minus 8y plus 4. Same thing for my x quantity. If I add 1 on the inside, there's really that minus 9 out front, so it's like I'm adding a negative 9, so I would subtract 9 to the right side as well. If you were to add 1 twice to the right side, your non-variable term would be wrong, and then when we complete the rest of the problem, you'd be your denominators for your quantities would be wrong, and you'll see how that works out here in a second. So again, whenever I have a factor or a number out front of my quantity and complete the square on the inside, whatever I add to the right side will have to take into account what that number out front of my quantity is. In this case, it was a 4 and a 9, so I had to put those numbers on the right side as well. So what I'd get is 4 times the quantity y minus 1 squared, that's me factoring that, minus 9 times the quantity x plus 1 squared equals 36. And the last step to make this standard form is I would have to actually make the right side equal to 1. So I'm going to divide everything by 36. And the 4 in the numerator of the y term and the 36 in the denominator will reduce and become 9. And the 9 and 36 in the second term will reduce and become 4. So what I have is the finished standard form hyperbola would be y minus 1 quantity squared over 9 minus x plus 1 quantity squared over 4 equals 1. This is about as involved as we'll have to get, which is coefficients other than 1 out front of x and y. I'd have to factor that out, complete the square, and then make sure you add the correct numbers to the right side, and then finish writing this in standard form. The next example is similar, but we're not going to be dealing with a hyperbola. So let's take a look at the next example here. So we want to find the discriminant and see what type of conic we're dealing with, and then write in standard form. So a is going to be 2, b is going to be 0, and c is going to be 3. 0 because there is no xy term. And then the discriminant would be 0 squared minus 4 times 2 times 3. So I would get 0 minus 24, which is negative 24. And since that's less than 0, this is the equation of an ellipse. So that should give me a clue as to how I'm going to write this in standard form. It's going to be pretty similar to the hyperbola example we just did. The only difference here is I can write my x term first or my y term first. Since there's an addition that's going to happen between them, it won't matter for an ellipse. So say I just put my x terms together and my y terms together, and then I'm going to move my 60 over to the other side. So I'd get 2x squared plus 12x plus 3y squared minus 24y equals negative 60. And then I'm going to complete the square, but before I do that, I need to factor out the 2 from the x terms and the 3 from the y terms. So I get 2 times x squared plus 6x, and I'm going to leave that little spot there inside that quantity for completing the square. And then I'd get 3 times y squared minus 8y, and then leave a spot there as well, equals negative 60. And then if I complete the square in the x quantity, I take half of 6 and square it, I get 9. and take half of 8 and square it, I get 16. And it should be a plus between those two quantities because we're dealing with an ellipse. So now, in terms of what I add to the right side, I don't add 9, I actually add 2 times 9, which is 18. And instead of adding 16, I add 3 times 16, which is 48. So now that those are perfect squares, I can write them as factored binomials. So 2 times x plus 3 quantity squared plus 3 times y minus 4 quantity squared is going to equal 6. And to finish this, I would have to divide everything by 6. And the 2 and the 6 were reduced to a 3, and the 3 and the 6 were reduced to a 2. And 6 over 6 is 1. So my finished answer is x plus 3 quantity squared over 3 plus y minus 4 quantity squared over 2 equals 1. So that's the process of checking the discriminant to see what type of conic we're dealing with, and that really just helps us see what form we were going to try and write this equation in. If it's a hyperbola or an ellipse, we want to keep all of our variable terms on one side and move our non-variable terms to the other. If it's a parabola, we want to keep our squared terms on one side and move everything else to the other. So it's really helpful to know what we're dealing with at the beginning, so it impacts how we approach the process of writing it in standard form. And I do want to make sure that writing these in standard form are going to be very completing the square focused, because that really is the only algebra technique to write these as quantity squared. We're not going to try and use the quadratic formula or go through that process. That would be very, very tedious and wouldn't actually lead you to where you want to go for these standard form versions of these. So that's day 7. We will continue to talk about all of these conics and putting it all together in the homework for day 7, and also as we review for our test.